Good. Okay. So, hi, welcome to the Robotics and AI seminar. So I'm one of the Dot champions. We hosted today. So, pieces of the back, there's loads. So, help yourself a lot and feel free to take a box with you because there's probably going to be a lot left. So, this is the seminar put on by the Dalton Institute, and thanks to people over there for organising. So, thanks to Rachel and Alice for helping put this together and ordering pizza in the room. Don't think there's any fire alarms planned today. Exits outdoor, and I think people left all right. But it's just across the way. So we've got two speakers today, Matt and Paul. We're both in the robotics group at Manchester. So first we're going to hear from Matt. We're going to talk a little bit about robotics for nuclear environments, and also give a bit of some of the other working groups we've got working in robotics currently at Manchester. So Matt is a robotics researcher with interest in developing a range of novel hardware. He gained his PhD in agile and dynamic robot locomotion from Bath in 2020. He then worked on the autonomous robot evolution project at the Bristol Robotics Lab, leading to the development of the robotic fabricator to automate the process of constructing physical evolved robots. He's now at Manchester developing radiation-tolerant robots for deployment in nuclear environments.
Great, thank you. Well, yes, great. So I have been sort of charged with the task today of giving you a quick overview of lots of the different robots that we have developed at Manchester over the last few years for nuclear environments. So I should just quickly say that most of this isn't my actual work. So, you know, credit to the whole group. I think that'll be obvious when I start. So I am very quickly I'm gonna split the presentation into two halves. A very quick overview of lots of different robots that have been made over the years with lots of cool videos, and then the second half, a little bit of a kind of deeper dive with some more detail into my own work, because I can actually talk about that with in a bit more detail. So we haven't got much time, so I'll just plow straight on. So many of you probably have heard of Sellafield. I think we can legitimately call it, that says the most hazardous place in Europe, I think. So possibly the most hazardous place in Europe. It's an old nuclear site. It was the site of the first ever commercial nuclear power station in the world. And it is home to lots of nasty environments with lots of nasty things in, many of which date back to the 50s, the 60s, and 70s, when they put nuclear material into places without any real plan of how they were going to decommission and tidy it all up. And now, many decades later, we're coming back to them and saying, yeah, we really need to clean this up. The estimates are that it will take 100 years and probably, I've heard the phrase 100 years and 100 billion pounds, but maybe it's only 70 billion, be a bargain at that price. So there are lots of these sort of complicated and difficult places that we need to go in, and there are lots of obvious reasons why we might want to use robots, like it might be quicker, it might be cheaper, and we might be able to avoid people getting doses of radiation, which is generally something that we want to do. So we've got all these difficult places, and we want to develop robots that will help us do them quicker, cheaper, and safer. So a lot of what our robots are doing, particularly at the moment, is inspection and sensing. So those are the relatively easy things to do for robots, and we want to be able to move on in the long future into much more into actual interventions in terms of dealing with things. But a lot of what we want to do is literally just driving around with some sensors in order to understand what's there. So as I said, a lot of these places, they threw things in there without really recording everything that's there. So we need to know what's going on first. Okay, so without further ado, let's get on to some cool, interesting videos. Oh, I didn't realize there's that sound. So Lyra is one of our most successful robots. It's only small, it's about this big. One of its great features is that it's quite cheap, because once you deploy them into somewhere like this, like an air duct, basically, it's full of nasty dust, particularly radioactive dust. Once it gets covered in that, we can't have it back again. it automatically becomes nuclear waste, the entire robot, at least low-level nuclear waste, maybe more. So it needs to be relatively cheap. And this was actually deployed into a real plate. This is not a mock-up. This is an actual duct at a nuclear site called Dounreay, which is at the very north of Scotland. They like to put them in the most out-of-the-way places. So this duct had lots of dust in it because it was part of the extraction system, and they didn't know what this dust was made of. And if in a nuclear environment you don't know what your dust is made of, then you have to treat it as the worst possible thing it could be. They have to treat it like it was all plutonium dust, which would be really, really expensive to decommission. So this robot was able to go in. You can see here, it has this little arm on top, and it could just take samples, swabbing samples, and then bring them out again. And they can analyze those swabs and say, what is the dust actually made of? And they realize that actually most of it isn't plutonium dust. Most of it is a bit less bad. And because it's less bad, that means it'll be a lot cheaper for them to clear it up in the end. So this little robot saved them, I forget the exact figure, but it was millions of pounds. This small deployment. So that's our real poster child of, look, we can save you vast amounts of money if you'll let us. Okay, so one of the other, this is another robot we've developed as part of the Tyrone project, which is all about mapping of the radiation. So again, it's about finding out where the radiation is in a particular environment. So this is not quite a real decommissioning environment, but this is a research reactor, which we can use as a sort of somewhat real environment with actual radiation in it. And at the top here, you can see this is a map of the room, and this is the robot that drove around in these different places. And the brighter colors you can see are the places where it's found, oh, there's more radiation here. And then a big part of this project was turning this map that doesn't really look very intuitive to a person into this map. So we developed all the algorithms to fill in the blanks and work out, oh, look, it's really obvious there's a place here and there's a place here where there's radiation. So this is obviously something that could be very, very useful for the nuclear industry when they want to do regular surveying of a place and just continuously checking that they haven't got contamination, which is something that they do all the time. And okay, so this is related to the same robot. You can see it's a very similar looking robot. It's been developed over the years. So this is about taking that process and instead of driving it around manually, how can we drive them, get these robots to drive around autonomously within these environments? And in particular here, you can see what it's done is, oh, this is supposed to be a video, never mind. It drives around, it finds where the radiation sources are, and then it avoids those radiation sources in the future. So as it's driving around, it'll realize, oh, this is getting quite hot over here. There's some radiation. So I need to continue exploring, but I won't drive right past where the radiation source is in order to reduce the dose to the robot so that the robot could last longer. Okay, this is definitely one of my favorites. So there's lots of these environments that are sealed up because they don't want people going in there anymore. So they've concreted them over. And the only access we've got is where they drilled a hole in the wall. Right. So this is made of cardboard boxes because this is just a mock-up environment where we were testing it. But they're usually concrete walls. You can only go in through this tiny access port like this big. But we want a robot that's kind of this sort of size that can drive around. So, of course, this guy can start off as this long, thin snake. It can drive through the hole, and then the video will change to see what's happening on the other side in a second. It kind of unfolds itself again on the other side, which I just think is so cool. So this is a big challenge in terms of the mechanical design of how you fit everything into this slot and then fold it all out again. It's also, you can see there's a lot of opportunities for some really unusual ways of moving here. So then that creates a huge challenge in how you control it and the software design. But yeah, but it should be able to fit around corners that a robot of that size wouldn't ordinarily be able to fit around. So this, yeah, definitely very, very cool robot. Okay, and this is called Karma. I think this is Karma 2, strictly speaking. So as I say, a lot of what they do day to day in these sort of nuclear environments is scanning places to check that there hasn't been any accidental contamination, particularly dust and that kind of thing. So this robot will drive around a room, and this grey box on the front here, which this is the slightly newer, shinier version, has been replaced by this grey box here, is what they call an alpha paddle. So it detects alpha radiation, but you need to get really close to a surface in order to detect alpha radiation, which is why it has to be like mounted off the front on the bottom. So that will scan the floor as it drives along. Before it drives over the floor, it'll scan it and make sure that there's no alpha radiation there. So this is something that they do all the time as people at the moment. They have people who walk around scanning the floor. So you might think, well, we can get people to do it. We don't really need a robot for that, which is sort of true. But the trouble is that the people who are qualified and trained to do this are in huge demand, and there's a massive shortage. So if we can get some robots to do the routine tasks, which are hopefully like the low-hanging fruit, like the easiest stuff for us to get robots to do, if we can get our robots in and convince them that, oh, the robots can do these jobs for you, then those people can go and do more important, more difficult jobs. And there should be a deployment of this later this month at Sellafield to hopefully show them the robot and say, look, it does work, it can do really useful things for you. That deployment has been in the works for quite a long time, I believe, but it's supposed to be happening this month, but don't bet your house on it. Okay, so those are all kind of ground-based robots driving around. There's also quite a lot of aquatic environments in these nuclear sites, particularly Sellafield, although it's very common to use fuel ponds, right, for all kinds of things. So at Sellafield in particular, they have a lot of very challenging aquatic environments that they call the ponds, nuclear ponds. So in the during the miners' strike in the 70s, I think, the country was really short on electricity because they didn't have any coal because the miners were on strike. And so they ran their nuclear power stations at max and churned out loads and loads of used nuclear fuel. They didn't really have anything to do with at the time because this kind of overwhelmed the capacity to reprocess all the fuel. So what they did was they went to these nuclear fuel ponds, these like massive concrete swimming pools, and they just started dumping them in the pools without really paying much attention and writing down exactly what they put everywhere. And some of the skips fell over and the fuel went everywhere, and they just went, oh, it doesn't matter, we'll worry about that later. We'll worry about that later. And now, what are we, 50 years on? It's now time, oh yeah, we really need to be worrying about this because the fuel ponds are starting to fall apart, which is bad. And there's also aquatic environments at Fukushima where they had a nuclear accident I'll talk about a bit, because some of them are partially flooded in the bottom. So we want to build some aquatic robots that can go in and, as I say, in the first instance, survey these environments, can work out what is there and what is going on. So this is one of the first aquatic robots that we made in the group, called Avexis, which is only about this sort of size, about the size of a football. So again, it can go down one of these access holes. And then you can see on this, on the right here, it's got these little jets that squirt out water for it to control itself and propel itself around. So that was one of our first robots and has been deployed in different places. But very, very simple. All it does is move around and carries a webcam. Now Mallard, this was so another robot that we've developed. This was originally developed as part of a challenge from the International Atomic Energy Agency, if I got that right, IAEA. So they said, well, what we want to be able to do is in a operating power station or wherever where they have nuclear fuel rods in a storage pool, what we want is a robot that can autonomously go around on the surface, and it can carry a special sensor that will be able to detect the fuel rods. So the IAEA want to go around and inspect nuclear power stations all around the world and be able to say, okay, you told us that you've got this many fuel rods in your pond. We want a robot that can go around and independently verify that you do actually have the fuel rods that you said you had, and they are where you say you are. So this was a challenge that we took part in and developed this robot to do this pattern around the pool. And then that has sort of developed on, so that instead of just thinking about going around on the surface, we also want a robot that can go underwater. And then when you think about, for example, back at the pools, it can go in and inspect them. But one of the great challenges when you're under the water is what in fancy terms we call localization, which really just means knowing where you are. Which seems like a really obvious and easy thing, right? Localization, but underwater it becomes really, really difficult because you can't use GPS, radio waves don't really work. So, we're developing this system here where MALAR, the surface vehicle on the top, does warn you where it is, and then you have an underwater vehicle, and we want to not have any communication between the two, because eventually we want the underwater vehicle to not have a tether. So it's a very simple system where you just have two cameras pointing at each other, and these sort of QR code tags on them. And then the real challenge is developing the algorithms so that the two robots don't drift apart from each other. So they both kind of compensate to make sure. So you can see here, when this robot gets given a tug, the surface robot will come over to meet it so that it doesn't get lost. Yeah, so you're never losing each other. So that's a big part of our work now, is developing aquatic robots and all the algorithms around how you control them underwater and don't lose track of where you are. Whew. Okay, that's a whistle-stop tour of lots of different robots with lots of different videos. So I've just got a few more minutes where I will talk specifically about my bit of work and all the more boring details. So I started here just under a year ago, which is slightly scary. And my project is all about developing a radiation tolerant robot. So you might say, you've just shown us a whole load of robots going around in nuclear environments. Aren't they all radiation tolerant? And the answer is yes and no. So, for example, at Fukushima, they had a little accident a few years ago. Things went a little bit wrong. And the fuel rods don't look nice and straight anymore. They're all sort of melted into a big mess. And the radiation around the melted fuel in the primary containment vessel, no one's quite sure exactly how strong it is, but we're assuming it's something around 1,000 grays an hour, which, for context, your human dose of 20 milligray a year, you'd get that in less than 1/10 of a second. So obviously people aren't going in there. So yeah, we're going to send some robots in. Obviously, that's what we do. But typically, if you just take a robot and build it without really thinking about radiation tolerance, you probably get a tolerance of about 100 gray, which gives you a few minutes in this sort of radiation field, which is better than a human, obviously, and it doesn't matter so much if you kill a robot, but it's not enough to really do anything particularly useful. So for these very high radiation fields, we need to think specifically about how we're going to make our robot kind of radiation tolerant. So to put that into a slightly more sciencey table, you've got less than a second for a person, a few minutes for a typical robot. And then my project, it's called Rhino for some reason. So we're aiming for something like at least 10 kilogray, which should give you a few hours, which should be long enough to, at least, as I say, kind of survey the area or do something useful. Okay, so the project is a collaboration between us, this isn't us, this is Lancaster, between Lancaster, who are experts in developing the radiation sensor that we will kind of carry on our robot, which will do the actual useful work. Otherwise, we're just driving around for fun. So that's kind of the payload. We have our colleagues in Japan who are experts in building what are called FPGAs, which are basically like a small computer that are radiation tolerant, because that's otherwise a normal computer would never work. And then we're left with building all the rest of it, right? So all of everything else that makes it a robot is down to us, all the robot hardware. Yeah, we're making everything else. So the official hypothesis for the project is wordy and horrible and terribly not written by me, I mean. But basically it comes down to the idea that instead of making our robot really complicated and then trying to make it radiation tolerant by adding lead shielding or whatever, which would be the obvious thought, you end up with a really big, heavy, cumbersome robot that's actually really difficult to use. So we want to instead strip back everything that we don't need and just find the simple components we can use that just are radiation tolerant or radiation tolerant enough. So the strategy for doing this, oh, that's the wrong button. So we're going to select some candidate components that might be useful. We're going to test them to see whether or not they're radiation tolerant enough for us. Then we might need to go back and select some new ones if they're not tolerant enough. But if they are, we can design our robot out of them. Okay, so what components do we need to make a robot? So as I say, Okuyama, our Japanese partners, are looking after the brain of the robot, will do the control. So we're left with having to find some actuation, which means some way that we can make the robot drive. We're going to need some power regulation, which means voltage regulators, which are a particularly susceptible area, particularly difficult. And then we're going to need some sensing so that once it goes around the corner, we can still drive it and know where it is. So I've started off with this half. So that's sort of what we're going to talk about today, is the actuation and power regulators. So that's component selection. Next up is irradiation testing. So there's a facility called the Dalton facility, DCF, which I'm sure many of you will have heard of. And there they have this great machine, the gamma irradiator, which means that we can take our components that we want to test, we put them in here, we remember to close the door, and we turn it on, and it bombards them with gamma rays, and when we see how long they last. Simple as that. So we did a 29-hour irradiation, which gave us about 50 kilogray, which, because it's a nice round number, 1,000 gray an hour, gives us, we reckon that would give us about 50 hours if we deployed it into Fukushima, which is long enough to do something useful, as I said. So I won't bore you by listing all the details, but we selected some different components, and lo and behold, some of them are nice and green, meaning that they survived. So we found some components we can use to make a robot. And then you say, are those components sufficient to make a robot? Well, yes, they are. So here's my CAD design. And then by the magic of PowerPoint, it turns into a real robot. So it's very simple. All it does is drive along at the moment, but we've demonstrated that we have enough components that we've proven to be radiation tolerant enough that we can make this little remote control robot that we could deploy. Okay, so that was this half of the of our diagram. So obviously we've done this. This is happening now. I just last week got some preliminary results from some sensors, and it's looking promising, which is exciting. Then once we have some actuators and some sensors, we should have a robot that we can drive around. Next is to integrate the FPGA from Japan so that the entire thing is radiation tolerant. Then we can add the sensors from Lancaster, and hopefully we'll be ready to take it along to these places and say, hey, look, we've got a robot that we know is radiation tolerant enough that it's not going to die. Yeah, so that's everything I had. Thank you so much for listening. Cool, I think, yeah.
Awesome. Thank you, Matt.
Yeah, you're welcome.
So next up we have Paul. We're going to do the questions at the end, just so that we're not overrunning. And also it might be questions that both of you want to answer at the same time, since there's quite a lot of overlap. So Paul's going to tell us a little bit about his work in robot cyber-physical systems and digital twins for asset management in nuclear environments. So Paul's currently the academic and technical project manager for Cradle, which is the Centre for Robotic Autonomy in Demanding and Long-Lasting Environments, which I think he'll touch on as part of his talk today. He gained his PhD in Leeds, looking at brain-computer interfaces integrated with virtual reality and robotic exoskeletons. He then started at Manchester in 2021 as a postdoc, working on cyber-physical systems and digital twins as part of the Robotics and AI in Nuclear Hub and Robotics and Nuclear Environment project before taking on his current role this year. So, over to you, Paul.
Cheers. Thank you, Will. Hi, good afternoon, everyone. So yeah, that was right. Before I became a project manager, I did a postdoc for 2 years. And that was part of the nuclear robotics work that we've done in the university with Dalton and with the Center for Robotics and AI. So just coming from Matt's talk about the robots, the challenge was when I joined the universities, we have these robots. Can we put a digital version of that robot and their environments that they're working with? So that's the major challenge. And so we've set out a course of these research and eventually not only have a digital version of each robot, but also an integrated cyber physical, so a virtual robot connected to a physical robot. But it is a hard task. So check. Yeah, so the outline is just, I'm gonna talk about the work that we've done for the past 2 years in terms of this space. It's relatively 3 major projects and 3 major papers or publications that we've been writing about, and of course, touch on other work by the center, the research group, and what's ahead, and that would be Cradle, which is a partnership with industry. So within all of these projects, if you've heard of REEG, Robotics and AI Nuclear, which is led by the University of Manchester under Barry Lennox. So I was working with Simon Watson on this space. And then after REEG ended, I transferred to RNE, which is Robotics for Nuclear Environments. And then with that, we had this sort of small collaboration with a few universities, which I'll explain later, which is called REEG. These are all like developing robot fleets. And now we have Cradle, which is the Center for Robotic Autonomy in Demanding and Long-Lasting Environments, which touches on nuclears. So, okay, when we say digital twins, there a lot of people are working on digital twins, but we tend to have a bit of a disagreement or non-consensus on terminologies and I guess terminologies on the whole space. But when you say, for example, in robots, when you say a digital twin, that can mean a lot of things. So you have a physical twin, which is the actual robot, right? But you can say a digital twin can be a digital motion or mock-up. So that means like you have your CAD, so you have your CAD models, which is an exact, not exact, like the whole dimensions and all of the parts are replicated in the digital space. But also you can connect that to a software where when your robot moves, the digital robot also moves, and that becomes like a sort of a digital shadow. And then you have real-time digital twins where you exchange sensor data, you can connect wherever, so the robot moves, the physical one and the virtual one moves with each other, and then you get some sort of real-time exchange of data or the sensors. For example, their IMUs, their encoders, and all of that stuff. So a lot of these can be called digital twins. And it's sort of just trying to navigate around terminologies and stuff. But when you also talk about digital twins, you can also talk about their environments. So for example, you have a physical environment, which is this sort of robotic space or a nuclear facility, for example. You can have a map of that digital twin, right? So you have a sort of 2D map of that floor plan. That could be a digital twin because, of course, if it's in the digital space and then you have that in your physical space, you can have that sort of arrangement. Of course, you can also have 3D digital twins where you have CAD models of the building or assets in that environment. But then also you can have 3D digital twins with environments with sensor data. So these are collected from cameras, LiDARs, all of the sensors that you got. So again, there's a lot of mix up with terminologies, but all of this can be considered one. Just to set the terminologies. And cyber physical systems is another term that we use in the digital twin research, and it's, I guess, the whole umbrella term when you connect a physical entity or robot or environment with the digital twin. So you've got the physical twins here, the robots, the environment connected to the world. You got the digital twins on the other side. But they're connected with sort of a term called digital tissues. So these are mostly what happens in terms of connecting these physical and digital twins. You can add a human element into this one, human in the loop, where you have the interfaces, the virtual reality headsets, the screens and stuff, or the haptics example. So all of that you can call a cyber physical system. And usually for this research, we tend to look at cyber physical systems for asset management. So like when you say asset management, when you go to a nuclear facility, you can do a lot of activities such as inspection, maintenance, and repair, and also relation to robotics. So that's what we looked at. And when you talk about digital twins, it's about, there are stages of development into it. If anyone has heard about AI and has so many levels on it, so you can call a machine learning model an AI, for example, or some sort. But then you have ChatGPT and learn LLMs, like large learning models, language models. So that sort of spectrum of AI development can also be applied to digital twins. So for example, a data twin and an asset twin are more like they copy what the physical and the digital does. But then you have, at the end of the spectrum, you have the cognitive twins where they do use AI, where they use all of this decision making based on sensors that are in the robot. So just saying in here, there are different stages, and we've not really achieved a fully fledged digital twin of a system, of a robot, because it requires a lot of work and it's still there in the future. We might have like some sort of predictive one, so they can predict with some sort of historical data. But yeah, we're working towards that in the future. So that's that. So how do you apply that in the nuclear environment, for example? So you have a cyber physical system for nuclear environments. Say you have Sellafield, for example, as a legacy nuclear facility being decommissioned, or it can actually talk about fusion engineering, for example, if you want a fusion reactor facility that would like to have some robots in it. So you have that. Of course, you will get digital twin from the sensors, and then you can connect simulation environments into it. And these are the work that I've been doing in terms of the technicalities of the projects in the university. Is that how you do a lot of sensor fusion? So the sensors that you get from cameras, from these radiation sensors, and how can you apply that to a simulation environment? So it's sort of like, I don't know, like a nuclear robot simulator, or if you've ever played that one in the games, like you are a nuclear robot, you have a health bar, and then how can you create, how can you play a game? So it could be like a training of some sort, or some sort of trying to mimic how the sensors would behave for any signatures when you go into this nuclear facility. So because a lot of my PhD has been in game development and developing simulations. So as my first task, I was sort of creating some sort of VR experience of a robot in a nuclear reactor and try to navigate around and try to drive. It's interesting. So you have that. And of course, a lot of this would, you would need a lot of the boring work, which I call it, because I'm not the network guy. I'm not a network engineer person. I've worked with someone who's more leaning towards that, and we've tried to investigate how much data is needed to do a lot of these exchanges of digital twin stuff. So what we did is that as a case study, we tried long distance teleoperation of a robot. So imagine yourself operating a robot in a nuclear facility at Sellafield or in Doonrame, Scotland, or somewhere in Fulham, for example. And you want to know how much of these data are being transferred back to your base station. We were in Sackville Street back then, in the university. And for example, the setup that we have is that from university, you go to a server in London and go back to Hale in Cumbria. So that takes a lot of, it's 200, more than 200 kilometers of distance, or 500. So how much of these are from a data metric consumes your processing time? So our setup is just using an Amazon cloud VPN with the VPN tunnel. So we use both ROS on both ends. And I was the one doing the base station. I was the one controlling the robot, where my colleague was in Cumbria, in near Sellafield, who has the robot. And we have this sort of two-way communication. So yeah, actually the total distance is 228 kilometers. And we're trying to map out the latency, the delay of the data from pushing a button of going to that facility and then going back to not only pushing a button, but also getting data. So like camera data and LiDAR data. So point cloud, for example. I don't want to worry with results, but just for a brief summary, what we found is that while we both experimented with wired and wireless connections, the point clouds really give you around 3 to 3 second delay in terms of transmitting data from mapping to this center. The odometry is a robot's sort of location in terms of its wheels. It gives you a bit of in milliseconds. So around, it's a bit faster, and also the joystick controller is a bit faster. So there's not really a lot of analysis in here. It's just us characterizing how much data is being transferred and it's needed by a single robot being teleoperated around 250 kilometers. And we did try this with me trying to operate a robot in Tokyo, Japan. It's the same. So I guess if you're trying to operate a robot in Mars, it takes 15 minutes, right? So but in the nuclear setting, 2 seconds is a bit much. Obviously, you wouldn't want to operate a robot in a live nuclear facility. So this is just a proof of concept. Yeah. So now you have one robot. What if you use a robot? Because that's what we want in robotics. We want to have a sort of we want to take over the world domination and stuff. So we want to deploy a fleet of robots in a nuclear facility, drones or some UGVs. Of course, it's not that realistic at the moment, but we're just asking a question of what if we want to increase that into a number of robots? Let's say 2 robots, 3 robots, 100 robots, if it's possible. And so the bandwidth consumption in the network requirements increases exponentially. And this is something that we wanted in this sort of work. We wanted to take account of this, the prioritization of data. Do you actually need point cloud at the get-go when you do the inspection or stuff? Or do you just want to drive this robot around? Because the motivation of this is, why do we want, again, like Matt said, like why do we want to send robots into these nuclear facilities? Also, why do we want the operators to be trained to send robots into these facilities? Is to increase their sort of capabilities of doing this inspection, or at least maintaining for a non-decommissioning setup, for example, infusion, for example. So that's what we set out for, and this is the next sort of project that we had is SREEG, which stands for Symbiotic Autonomous Robot Ecosystems for Sustainable Environments, a bit of an acronym. But what we want is that post-COVID 2021, we set up the challenge for the University of Manchester, Glasgow, Bristol, and our partners in Sellafield and REEG to meet for the first time since COVID. And we've been talking online, and this is the first time that we met. We had led 32 researchers into this new facility in Whitehaven, Cumbria, which is a mock-up nuclear practice bed, really new with Sellafield and UKAEA and NDA, the Nuclear Decommissioning Authority. And so we set out to build a fleet of robots trying to perform inspection, maintenance, and repair for a nuclear site. So the output of that led to a lot of research work. And now we've just recently published this paper in our lessons learned for nuclear, deploying a robot fleet in nuclear environments. And there's 2 more papers coming out of this sort of technical sprint. So it's a sprint session where we were there for 5 days doing nothing but just deploying some robots. Let's see one of the work that I've led in terms of the output of this one. It's called the digital twin side of that robot fleet. So you got an actual robot fleet, the physical one, but what about the digital aspect of that? So you have a lot of authors, but one thing that we did here is that we have a group that focuses on developing digital twins. And so this is in collaboration with Bristol. And so what we did is that we developed the interfaces for the point of view of each robot. So this was inspired in some first-person shooter games, for example. If you played some of these ones, you got a health bar in it that stands for your battery, but also you got this mini map where you can see how you're going to develop the mapping of the robot in terms of the LiDAR and all of the assets, which we call in construction as BIM, or building information model. So you have the CAN models, the assets, all the sensor data. You've got glove boxes, hazards, and stuff. And in collaboration with Dr. Andy West from the ROAN project, we've got the radiation mapping of this translated to point cloud. And we use a software called Unity, which is mostly a game engine. So you develop games there, but you can also use that to connect the robots. So get the physical robots here, and I'll show you a video, which each of those have their own robotic software, mostly in ROS, or Robot Operating System, but that's connected through a network connection within the same system to the Unity platform. And that Unity is how we use it to be interfaced in the flat screen or a virtual reality headset. So this one is sort of a robot fleet management system. So imagine you're in a nuclear facility and right now, one person controls one robot, but what if there's one person who can try to control a robot fleet in this scenario? And, again, this was inspired in some strategic games. To play Red Alert, or I don't know what those some of them are, but it's like pointing at one point to another. Go teach this robot to come here and teach this robot to come there and stuff. Again, these are all simulated autonomously. So you got this first-person view, you got the 3D map, you got the mini map as well, and so you have a sort of thing that is that. These are more structured in terms of the nuclear inspections. So when you look at other facilities, you know, like for example, a decommissioning facility, you know where the bits and pieces are. It just changes. It is a dynamic environment. So how would you account for this environment? And usually people do a lot of inspections, but can you inspect it from afar? And stuff? Of course, this is different from other facilities who've done, for example, disaster response, like in Fukushima or Chernobyl, for example. You are trying to map out unstructured environments. And so this is a different issue. So this is what the output of it was. And yeah, we're still writing a paper about it, actually. That. Right. Another thing is that with collaboration with Dr. Andrew West, and we've got the summer student who is from MMU and doing game development. So we've got that assets, but can we make it more photorealistic? Because I think it's better. It looks nice and it trains a lot from the image recognition systems of the robots, but also in terms of the training that you have. If you are immersed in a photorealistic scenario, 3D digital twin environment, then you'd have better understanding of corrosion, for example, of degradation of materials and all of the assets that you have. So we tried in the summer student project, Maddie, she is using Blender to use a lot of this to generate and render some of their photorealistic stuff. And there's a wish list in the group of nuclear roboticists where we want more clutter, we want more, we want a lot of, I guess like all of these assets and stuff so that we can use it in our simulations. And this is available for everyone to use actually. Just contact us or the toy contributors. It's in GitHub. Actually. And then using that, we've got an interface. I was able to go to Nara Fukushima, which is just within the exclusion zone, a 20-kilometer zone around here of the Fukushima prefecture. They have a facility here that is similar to what Reiko is, right? Which is trying to be a mock-up of a nuclear facility. So they have a lot of robot deployments and stuff. It's an amazing experience, and it is through the NEST fellowship scheme, which is nuclear education skills and training, which I think we're trying to market with in terms of the robotics work and the nuclear radiation work. And it's a sort of an exchange where postdocs, PhDs can go to Japan or I think for Manchester, we can just go to Japan, and then we can also have people from our partners in Japan Atomic Energy Agency or JAEA do our work in here. So what I did there is that I used the interface to get robotic operators to try to learn the system and see whether the heuristics of it, they liked it, they don't like it, it's not usable, or is it usable, and how can we improve that system? So that's that. And of course, this is a fun experience for everyone. And now, just to give you a glimpse of the future, is that we're continuing the nuclear work of robotics and digital twins through Cradle, which is a 5-year prosperity partnership with Jacobs, the engineering firm. But Jacobs has a lot of client portfolios, not just nuclear, they do space, they do urban infrastructure and stuff. But one of it is their relationship with a lot of the nuclear facilities and agencies here in the UK. And we're trying to recruit a lot of 14 PhD students, 10 full-time postdoctoral researchers, and it's a core research program led by industry. Actually, one of our PhDs is in here. We have Josh, who's working on a radiation sensing robot. So that's the outlook, that's the output and the future of our work here in terms not only in digital twin space, but also in nuclear robotics. So that is the end of my talk. Cheers. Yeah.
Thank you very much.
Thank you.
We invite Matt back again. Yes. Any questions? That's okay. So, do we have any questions online during the chat? Do we have any questions from the group?
What's the most challenging part about doing a deployment within the nuclear industry?
I have anybody.
Are we still being recorded? You go, Paul.
Okay, yeah, well, so one of the biggest challenges, of course, is you have to create this sort of assurance and trust case with them. They wouldn't
That's
want.
what I wanted to say.
So just to, I'm not sure if you know about this, but the story with Lyra and Doomray is that Lyra is supposed to be connected wirelessly, right? So The only challenge is that they wanted to deploy that robot in a dock that was not visited for around decades. And the struggle of that, and I think it got postponed again and postponed, but then they allowed it, is that there's no assurance that when that robot fails, how is that going to be retrieved? And they don't want a robot graveyard in that nuclear facility, for example. So what they did is that they put a tether in it so that they can pull it. So yeah, that is the
Yeah,
wire.
it pulled the cable along with it, which didn't have any purpose, except that if the robot broke, they could just yank it out.
Yeah.
Which,
But yeah, it's hard to prove assurance as well in a proof of concept. So it's a massive work, and that's why in Pega we have an assurance person. So, but
yeah, I think it takes a lot of time and effort to get people to trust these systems, right, and become comfortable. Though it's interesting. We visited Sellafield yesterday, and they sort of hadn't let their work in the ponds at the moment, where they're trying to consolidate everything and eventually get the material out. They have started using what they call ROVs, the little underwater remote control vehicles. They use them every day. So they have started using them, but it takes years and years to build up that confidence and that trust in from the users that these systems are actually useful and reliable enough for them. So yeah, because it's very easy as researchers to do something in a lab and you kind of get it to work once, you make a video, you write a paper and you plot your graph. But that's quite different from these sort of real world environments where they want it to be really robust and reliable and work day in, day out. And as Paul says, if they break and they're in a nuclear environment, particularly one that's difficult to access, then they just become a much bigger problem than they were ever, solving. So it's all about reliability and that sort of trustworthiness of the system. Yeah, I think that's our big challenge.
As a follow-up from that, is there any issues in terms of regulations? Because obviously the nuclear industry is really heavily regulated.
Yeah.
Do you have, or are there regulations in terms of deploying robots, whether they're human controlled or autonomously controlled?
I think everything is done on a case-by-case basis, as far as I know. So you have to prove your safety case every single individual deployment. And as far as I'm aware, no one's ever done anything autonomous in any live nuclear plant. They're very much shy away from anything autonomous.
And this is a big research theme in the University of Manchester, that in the computer science department, we have an autonomy and verification group looking into nuclear actually. So that's part of the REEG, that was part of R&D as well, and now it's part of Hale. So yeah, we're continuing on that conversation, making sure that it's not being lost as well. So yeah, that's with Louise, Dennis, and my conclusion.
Anika?
Sorry, I'm usually comfortable to work with like I can make. But me, I'm quite interested. Obviously, your robots are exposed to radioactive waste at different levels. What's the kind of lifetime of robots? Is it very different from the application?
Yeah, that sounds extremely relevant. So the answer is it depends. Depends enormously, because some of these environments, any of these environments where at the moment they have people in a paper suit, the radiation levels are just not going to be enough to destroy a robot, ever, pretty much, in a practical lifetime. But then there are some environments where the radiation levels are really, really high. And typically a robot might last only maybe a few hours even. And then there's anything. So that's actually the topic of my research is developing a robot for the very high level radiation fluxes. But it's not just radiation, of course, it's all the other sort of things that go along with it. So again, something else I learned at Sellafield yesterday, my new fun fact is that for their underwater robots, at first when they deployed them, they were really worried, oh, is the radiation going to kill them? But the radiation hasn't been a problem whatsoever. What has been a problem is that in the water, they put this salt that I've forgotten the chemical name of, and I apologize for any chemists in the room, but they put this salt in that absorbs some of the radioactive element, they put in clay that replaces the radioactive elements with some other salt. But anyway, that ends up with the water being really, really alkaline. It's like pH 11. And so then they put these robots in, and actually that's the thing that's been killing them. You know, they eats all of the CO2 things. So it's not just the radiation, it's all the other things, you know, that go along with that. But yeah.
Yeah, I think this is a computational related question. So, you know, we transfer every sensor data to the planes.
Yeah.
But it's kind of a decision that the robot drive automatically or use the cloud service from the supercomputer to help you calculate the strategy control the robot.
Yeah.
So is any plan for like switching both mode or?
Yes, that's actually a good question. So yeah, again, with the data prioritization one, so why don't you just leave the processing in the supercomputer or the computer that has a lot of that? So that's something, so when you wanted to operate on that one, so you got that sort of operation data exchange, but then leave the processing to the later bits that you don't need at the moment. So and that's something that we are trying to work with, and I think in the future that could be a feature where you can try to just check which of the data are you needed in that instance, but then also how you can process that in the future. A lot of that can also be solved with AI and all of that, because you can just try to downsample some of the data, make it turn into a really fast, transferable one. So reduce the bandwidth. But then also we've just got one new person coming in who's much of the data guy, Philip Shah, who's joined the computer science department for the Center for Robotics and AI. And he's looking at a lot of this data minimization and data prioritization in terms of digital twins and teleoperation. So yes.
It's a question I'm facing now.
Oh, really? Yeah, maybe we can connect you to it. So yes.
Awesome. Well, thank you very much. We thank the speakers again. That ends sum up today. It's 2 o'clock. There's loads of pieces at the back, so please take the needs.